All right, good morning, gentlemen. So, as you know, I recently changed how I'm structuring the class. I've noticed, at least this week, we've been having a lot of technical issues. And so, my new plan is we are actually going to be doing something I'm modeling off of another teacher, where when you're in person, you'll be focusing on doing labs and a lot of hands on activities in the classroom. So, completing labs that might be like an extensive amount of time. And then when you're online, you'll be watching the lecture. Now, for my students that are 100% virtual, I have recorded labs. However, you will always begin the week. So, for example, when our blue cohort is in person, you will begin with a lecture. And then at the end of the week, when we switch, you will be watching that lab. So that's the new plan. Now, if you have any questions, please reach out to me. I am here as a resource for you, and I know that we're going to be really modeling it the next couple of days. But I'm hoping that this is more successful. And eventually I'll be plugging these into Edpuzzle so that way I can check for progress while you're watching it. However, for a lot of this first information, you might not have as many questions in the Edpuzzle. So just know that in the future, we will be using Edpuzzle quite heavily when we're doing practice problems. So you have the opportunity to put the answer you get in before I go through. So that way I know you completely understand it and you completely understand the concept. So that's the plan. However, you will still remain on Zoom. So if you have any questions, you can ask me. I'll assign some homework, and I'm giving you a week to do a lot of those assignments. So you have an opportunity to come see me in person, or we can set a meeting up. So that way you don't have any late assignments, but that way you can really grasp what you're learning. So that way, if you really need to practice it in the lab to get it to click, we can make that happen. But that's the plan. So today, the lecture is going to be reviewing graphing. I'm going to be showing you how to use your scientific calculator. Please excuse me, let me grab a couple. I'll be showing you how to use some calculators. And if you do not have one during this lecture, that is fine. Make sure you get one as soon as possible because I'm planning on us having a quiz next week. And it's important that you have a calculator. So that's the plan of the lecture today. You will have some homework. It's going to be a basic skills worksheet, so you'll have a week to complete it. It's a lot of review, a lot of math, and I will probably ask you this question. I'm posting it on Canvas, but I am fine and comfortable if you know how to upload it to, say, Notability to write it out, or you can type your answers. It's really up to your comfort. So let's review the scientific method. I'm going to move my video down a little bit. Okay, so the scientific method, the goal of it is to design an experiment. Cool. To design an experiment that answers a question that can be repeated and will produce reliable results. And when we're going through this, we have two types of variables to come out of it. We have an independent variable and then we have a dependent variable. So that independent variable is what we do. It's what we change. We manipulate that variable. And our dependent is what we measure. So it's something that responds to our independent variable. So for example, I'll have some that we'll go into, but I can use plant fertilizer and track the growth of plants. And I'll talk about the different variables if we were using that as an experiment to really explain it. A control is something that's kept the same. So an example is I can alter something in an environment, a plant for our example, excuse me. So if I add more fertilizer, my responding variable is how much that plant's going to grow. But the control that I can have is I can keep it in that same room, same kind of consistent temperature, consistent environment. So that way it's responding to just the fertilizer and not surrounding variables that are out of my control. I'm controlling the environment that plant's in. Changing the fertilizer and tracking the growth, which is a response to me fertilizing it. So let's do some practice. So we're going to do number 1, and then we'll do number 2, number 3. I'm planning on having this in an ed puzzle, and you'll type what you think is correct. So a study is done to test how much longer a new battery will last compared to an older version. So I'd have 2 variables in this study. I'd have an independent variable and a dependent variable. So for this one, I'm going to go through what it would be and why, and then you guys will practice the next 2. So our independent variable is actually our different batteries, and our dependent is time. And the reason of this is that our independent is I'm changing the batteries. I'm including new batteries. I'm doing an older battery. So I have 2 batteries I'm testing, and I want to know how long they last. Well, how long they last is dependent on the type of battery. And so I'm changing the battery, tracking how long it takes for them to last. So now you're going to do number 2, which is a study is done comparing how effective bleach is at killing bacteria. So take a moment and tell me what the independent variable is and the dependent variable. All right, our independent variable is our use of bleach or not, because we're comparing how effective bleach is at killing, and our dependent variable is bacteria. We're taking away bleach, or we might be using a different brand of bleach, but we're studying how effective that bleach is at killing bacteria. So our bacteria is killed by the bleach, but we're changing the bleach. So now our last one is research is done to test if spending more time practicing chemistry problems increases grades. So take a moment, figure out the independent variable, dependent variable, and then I'll tell you them. Okay. So our independent variable is our amount of time doing our practice, and our dependent is our grade. So you're taking more time, less time. You really alter how much you practice your chemistry problems. And if you practice them a lot, you'll have a good grade. If you don't practice them a lot, you might not do so well. So our grade is what's fluctuating with the amount of time we focus on chemistry. So in a controlled experiment example, which I kind of talked about, is does fertilizer help plants grow? So our independent variable is always the amount or the type of fertilizer we're using. So we can use different brands. We can do more fertilizer, less fertilizer. That's something we can change. We can alter the amount for the experiment. However, our dependent variable will be the plant height. And our dependent has to be measurable. So I can measure a plant's height, but I could not measure maybe the amount of roots that are growing underneath, because it would require me taking it out. It'd be a pain. You really can't track that measurement well. So being able to have a visual measurement, very nice. Our control would be, we would use maybe the same type of plant for all the tests. I would use the same soil for all the tests. And I would also have the amount of sun equal for all of them. So I can control, they're going to get 6 hours of sun. It's going to be curly grass as the plant, and I'm going to use garden soil. I can use that because I can get a big bag. I can get 6 plants in a container, and I can put them in a little greenhouse and go, all right, this is my controlled environment. Nothing's going to change there. The only thing that I'm altering is the type of fertilizer or the amount of fertilizer for each plant. And I'll measure that height. But they're in the same environment, so I can get accurate results. So, independent and dependent variables. When you're making a data table, your independent is in the first column in a table, and your dependent is always the second column. So an example is my independent, I'm changing the time of what I'm studying, and I'm measuring the mass. The mass is dependent on how much time goes by. So an example of that is we're going to be doing a candle lab, and while I light it and time goes by, obviously it's going to be burning some of that wax, so the mass is going to go lower. So the mass is not going to really change a whole lot. It's just being manipulated by hi, I'm burning this candle for this long, this amount of time. Now, when you graph that, your independent, so always your first column is your x-axis, and your dependent, your y-axis. So no matter what, independent x, y is always going to be your dependent. And it's horizontal. And a good way to note is typically the independent value you're increasing over certain increments of time. So that way your y will fluctuate based on how it responds. So graphing skills, you need these on the ACT. So this graph below best represents the relationship between concentration and temperature for which of the following substances. So I want you to take a moment and I want you to respond to this question. So, yeah. I'll talk about this further, but I want you guys to just understand. I'll make a note in the ed puzzle for you so I don't blow it up with a big answer. But yeah. So our direct relationship is our positive slope. That's what it's called. It means it's increasing. So it means both sets of numbers in a table are increasing, which you can see when you look at the graph. So it's an increasing. So as I add more grams of fertilizer, I have a higher amount of growth for each plant. My indirect relationship is a negative slope where one set of numbers is increasing and one is decreasing. So for example, I'm adding more fertilizer. However, I don't see an increase in growth with the more fertilizer I add. So it's kind of that opposite. So it causes, while my x is increasing, my y will slope down. And my flat relationship is where there's no slope. So one set of numbers is increasing, but one stays relatively the same. So while these numbers may not be exactly the same because they have different decimals, they are similar enough that it produces a straight line because I'm not seeing an increase nor a decrease in the amount of fertilizer I am adding. So the general trends for you to know is that your direct relationship is where both values, our x or y, change in the same direction. So they're both increasing. Where our inverse relationship is one value goes up and the other goes down. So I see that opposite reaction. And my flat-lined relationship is where one value increases but the other stays the same. In that case, my variables are not related. But I see a constant relationship in that flat line. So why do we graph? When we graph, we're trying to identify general trends. And these trends are always using line graphs. And it's specifically, we're always going to use line graphs in chemistry. Cool. We're never going to use a bar graph or a pie graph. We always want to see and visualize a trend in chemistry. So you will be using line graphs exclusively, unless otherwise specified. When we're doing this, we're trying to identify and eliminate any outliers that might be in our data. So we'll kind of talk about outliers, but again, it's data points you really just can't make sense of. Sometimes something happens, you get really weird data, and it messes up all your like other data. So an example is I could have one plant that just for some reason doesn't want to grow, even when I'm adding fertilizer, because maybe the root system is dead or it has root rot. So it's going to inhibit its own growth. So I can't control that. And that's not something that should be counted in my complete data set because it's something that it just happened. So I want to be able to identify and eliminate those so that way my data, I'm getting like precise and accurate data. I'm not getting something that's like, oh, hey, I had all this beautiful data, but then I have this one that's all the way in the corner. What the heck? This also allows us to predict our best line fit. So when we're using our best fit line, we can predict something even if we don't collect data for it, because we can identify the trend and say, oh, well, if my plant gets more fertilizer and it increases in height, if I added 20 grams of fertilizer, I should see an increase in that height. a substantial increase when compared to our 10 grams and our 2 grams because I see that best fit line. So here's the parts of a graph. You have your x-axis, which is your independent variable, and you always label these with values and units. So if I'm doing time, I have to label with minutes. That is important. You will lose points in labs if you do not label your graphs with the units. Your y-axis is your dependent variable, again, labeled with units. And then you always label them name unit. I'm going to say that this is your only warning. If you give me a graph and it's not labeled, you will lose points. Your scales on an axis must increase at a constant rate. So I cannot go, oh, I'm going to do 5, 10, 20, 35, 40. No. If you're going to increase your axis, you have to have it consistent. So, for example, this bottom has it going up in increments of 5. Whereas right here, they have it going up in increments of 4. But they have our little ticks here, so that way you know where you're ending up. Your values must increase on both of the x and y axis. You cannot go backwards. You cannot go 0, -1, -2. They have to show an increase. And your numbers will always start at 0 and go to larger numbers. So no matter what, that center, like that point where they meet, the axes meet, is going to be 0. Your best fit line is your average representation of the trend. It's not a dot to dot. So you're not connecting your dots. You're just going to, which I'm going to use my board. Please excuse me, I need a marker. So when I have a data graph, I'm going to move my chair, excuse me. So when I have a graph and I collect data points, my data points won't always line up nicely. So, can you see that fine? Beautiful. So I might get a data point here, I might get one there, and around. So that's kind of not great. So there is my graph. I have all my data points, but I can tell I have a general trend. I see an increase in my trend. So I want to show that, but I am not going to connect my dots like that. I will not do that because that's not showing my trend. That's not my best fit line. It's kind of like when you buy a pair of jeans. You buy your jeans and you're like, oh, it fits nice here, but maybe my legs are too long, or maybe it's too loose on the legs. You're not going to find the perfect jeans that are going to fit you exactly. You're going to find the best fit for you. So maybe your waist might be a little big, but your legs are nice and long, so it covers your ankles, and your legs are comfortable, so you'll just wear a belt. It's kind of like that. So I see my trend, and I'm going to make my best fit line. Typically, you'll use a ruler, but I apologize. This is not going to be a straight line. So I find where it meets the 0, and I make my best fit line. Hope you can see that. Beautiful. So I show my general trend with my best fit line because it fits with the trend I have. So another thing is that you might notice in these graphs here that you have a couple outliers with your data. Your best fit line won't account those because you have that general trend already. So they're just those data points that are outside the best fit line. And those are how you know, like, hey, there's my outliers of data. Now, how could you predict how long an entire candle would take to burn? So use your best fit line and extrapolate the data. So based on the trend that you see, what can you predict? So please record your prediction down. So in this case, the graph would not be used. However, we have a French mark and a German mark that's like present on this graph. But in this case, you can tell and say, with an increase in French marks, we should also see an increase in German marks. So you're able to extrapolate. If I move up and let's say I move to 90 and I want to know how many more I'll have, you can use your best fit line and it will come up. So you can kind of give a rough estimate of like, hey, potentially 92. Gotta move you guys back. Oh goodness. All right, moving on from graphs. If you have any questions, email me. We're going to talk about scientific notation. So this allows us to write very big numbers and very small numbers as well. So every number written in scientific notation has three parts. We have our coefficient, we have our base, and we have our exponent. So our coefficient is typically, that's the number that we find that might have a billion decimals, and we don't want to have a billion decimals, and so we move over that decimal point, and so we show it by multiplying it by 10 and having that exponent raised to how many decimal points that it has. So your coefficient portion though, those only can be between 1 and 9.99. You can't have a 10 there. It has to be present between those variables. All right, calculator addition. Remember, these are our approved calculators for class. So these are the ones that you will be using. And this is what our exponent looks like. So I'll show you how to do that on each calculator. So you do not want to use your operator buttons for times 10 to the x. So what I mean is I don't want you saying multiply 10 exponent caret x in a way. What you're going to do is, like specifically on this calculator, you're going to look for EE or second EE. So on this calculator specifically, oh goodness, I have a second button, oh goodness, second, and then I actually have my EE right here. So in the case that I would use exponents, I would hit 10, second, EE to make this E, and that E stands for exponent, and then I would put in my exponent. In that case, I'm going to do 8. In this calculator, which I need to look where EE is at, a lot of these calculators are very funky. Cool, fantastic. I will look into this calculator a little more. However, do I have... Okay. So I'll look into this calculator more because maybe I am just forgetting. Oh, maybe that might help. For you, because a lot of this time using the same calculator, there's a lot of practice with it. So I'll look into that. However, you're going to use your EE button or your second EE, so you should be familiar with your calculator, but it's very similar to this. And then you're always going to use your change sign for a negative exponent. So what I mean by that is you'll never hit -2. You'll use this button down here to make your number negative. This symbolizes, excuse me, your negative button, whereas the subtraction sign implies that you're subtracting two numbers. So make sure that when you're using a negative exponent, you're using the change sign, not your minus button. And that is all I have for you. Again, I'm going to look into this calculator a little more, and I will let you know once I figure it out. However, I'm going to go back. Oh, I could just do it there. So if you have a TI-30XA, your EE button is right here. I'm going to figure out these ones. These are the class set. But you don't have to hit second EE. You would just hit the EE button here. Whereas on this calculator, you're going to hit second and then EE to open that up. You can also use the caret button to create an exponent as well. So if you have any questions, please feel free to email me and reach out. Your homework assignment's posted to Canvas. It's our basic skills worksheet. You can either complete that using Notability, or you can complete that on Canvas and just plug in your answers. I will share the answer key with you next week, so you may go over it. But you do need to submit your assignment before seeing that answer key. So until I see you again, have a wonderful day and complete that homework assignment. Bye.